Okay, so in this little lecture video, we're going to review a little bit about what it means to be an acid and a base, particularly with regards to water. So we know that an acid, you can actually have multiple definitions, is anything that donates a proton, an H+. You could also say it's an electron pair acceptor. And you can say it's something that produces H+ when you put it in water. And really we know that instead of produces, an acid actually releases an H+ when you put it in water. A base, on the other hand, is sort of the opposite definition. So it's something that accepts H+ from an acid. It's an electron pair donor. That's how it's able to accept the H+ from the acid. And it also produces hydroxide ion when in water. So produces, that's one word. Sometimes this is hard to write on. Produces OH- in water. Now it doesn't have to release it. So for example, we know that if you take sodium hydroxide and you put it in water, I'll just put water over the arrow for now, you know it breaks apart into aqueous sodium cation and it releases the hydroxide directly. That OH- is part of the molecule. But it doesn't have to be that way. You just have to produce hydroxide in water in order to be classified as a base. So the best example of that is ammonia. And we can see it clearly when we react ammonia with water. So when you put ammonia in water, the ammonia, or specifically the lone pair of electrons on the nitrogen, will accept an H+ from the water molecule to make ammonium, NH4+. And what's left after you take that H+ off of your H2O? Hydroxide. So in this case, ammonia doesn't have an OH- in its formula, but it produces OH- when you dissolve it in water, therefore classifying it as a base. So another shorthand method we can use to look at this would just be HA. So water, which is also a weak acid, we know that water is amphoteric. It can function as both an acid and as a base. But as a weak acid, if we're talking about those properties, we can also talk about the Ka of water. So if we take a water molecule plus another water molecule, one water will act as an acid, the other will act as a base. So you end up with H3O plus, that's a horrible oxygen, but that's okay, plus hydroxide ion. We could write the Ka value for this. So again, products over reactants. So in that case, we would have concentration of hydronium times concentration of hydroxide. And in this case, we know these guys are both liquids, whereas these guys are aqueous. That's why we included them in the Ka value. So there is no denominator in this expression. So we just have the concentration of the hydronium ion times the concentration of the hydroxide ion. So in this special case of water, the Ka is also referred to as the Kw. And that's the ionization constant of water. And at 25 degrees Celsius, so at 25 degrees Celsius, this value is constant, and it has a numerical value of 10 to the minus 14 molar squared. And you know with equilibrium constants, we always drop the units because they get really confusing and different. So we know then that if this Kw value is always constant, that if the concentration of the hydronium ion is equal to the concentration of the hydroxide ion, then they each have a value of 1.0 times 10 to the minus 7th molar. And we know at these concentrations, we call that solution neutral. There are equal amounts of both acid and base present. And then we know, of course, that if there is more hydronium ion present than hydroxide ion, then we now have more H pluses floating around. That is an acidic solution. And vice versa, if there's more hydroxide than hydronium, we now know we have a basic solution. But nobody really likes to talk about the concentrations of hydroxide and hydronium because those are very, very tiny numbers. So for practicality, again, we use a logarithmic scale. So we know that pH is the negative log of the concentration of the hydronium ions, or the concentration of the H plus. And we know then that we end up with the general pH scale ranging from 0 to 14. 7 is neutral. Up here we're basic. Below 7 we're acidic. But what's important to remember is that if you change the pH value by 1 unit, so if you change pH by one value, 1 unit, so if you go from 7 to 8 or 7 to 6 by 1 unit, that is a tenfold change in the concentration of H plus. Okay, either up or down, depending on which direction you're going, because this is a logarithmic scale. So when you change the pH by 1 unit, you're changing the amount or the concentration of H pluses floating around by 10 times that. Tenfold change. So now we're talking about pH also being really critical to biological function, because with those H pluses floating around, you start changing the protonation state of all of those acidic groups. And those have structural implications because you have ionic interactions, you have hydrogen bonding, and there are chemical considerations because now you have reactivity due to acids and bases. So since changing the concentration of H plus is so important, or so has such a large effect on biological structure and function, that's going to bring us to our next topic, which is that of buffers, solutions that resist changes in pH so that you don't have these wacky changes in structure or chemical reactivity in your biological system.